Let's start in 3 minutes.
Great, so I think I'll start now. Okay, so welcome back. Today I'll be going through divisibility number theory. So before I start going through the problems, maybe I'll just like briefly run through like the common ideas and techniques that you need in divisibility. So we have divisibility. Okay, so as you can refer to like the handout, the first idea that we use is um, Fermat's little theorem. Or we call it FLT. So Fermat's little theorem states that a to the power of p is congruent to a mod p for all primes p. So you may be asking, when is this theorem useful? So an instance where this theorem is useful is when you have like m to the power of n, where n is like a big number, right? And we're considering a mod of a prime. So if I asked you what is 2 to the power of maybe 61 mod 31, like how would you be able to like um derive like an answer? So the way you would do it is basically by Fermat's little theorem, we have that 2 to the power of 30 is congruent to 1 mod 31, right? Because this is equivalent to a to the power of p minus 1 is congruent to 1 mod p as long as p does not divide a, correct? So if we have this very useful condition, we'll be able to find what this is mod 31, right? Because 2 to the power of 61 is equals congruent to 2 to the power of 60 times 2 mod 31, which is basically congruent to 2 to the power of 30 square times 2 mod 31, right? And since 2 to the power of 30 is congruent to 1 mod 31, this is just congruent to 2 mod 31. So this is a very basic example of how Fermat's little theorem is used. So you can think of it as a way to reduce the power of the number mod a prime. The second one I brought up is Wilson's theorem, which states that p minus 1 factorial is congruent to minus 1 mod p for all primes p. Okay, this isn't as common as Fermat's little theorem when it comes to Olympiads, but then it is a very important theorem, especially when they ask for the modulo or like congruence of a factorial mod p. So whenever you see some sort of factorial and you want to evaluate it modulo a prime, the first idea that should come to mind is Wilson's theorem. Okay, so apart from the two main theorems, we have this fact, which is for a b larger than 0, a divides b implies that b is larger than or equals to a. And this may seem like a very like trivial or like very obvious fact, but it is actually a very useful tool when it comes to questions because it gives you a sense of the size of the number. So I think a lot of people were discussing question 1 of the problem set, and actually question 1 uses idea number 3. And a basic proof of why this is true is because if a and b are larger than 0, we can write b equals to ka, where k is some positive integer, right? And since k is larger than or equals to 1, it means that B equals to KA, which is larger than or equals to A. Which is like a very obvious condition, or like very easy to prove, but then it's not very easy to think of using when you're trying to solve the problem. And the last fact is GCD of AB divides MA plus NB for all integers Mn. And this is true because GCD of AB divides A, and the GCD of AB divides B. So any linear combination of A and B will be divisible by the GCD of A and B. Yeah, just in case you don't know what GCD is, it is the greatest common divisor. So, for example, the GCD of 8 and 6 is 2. So it's basically the largest divisor that divides both numbers A and B. So this is 2 times 4, and this is 2 times 3, right? And 4 and 3 don't share any common factors, so the GCD is 2. Yeah. So this is basically a summary of like the main ideas that we will use in divisibility questions in number theory. Okay. So let's move on to going through the problems that we have today. I think I saw like a lot of people trying problem number 1 in the general chat. Okay, so question 1. We have that find all A, B such that A divides B and A plus B plus 1 divides A squared plus B squared. So when trying this problem, what were your like ideas? Like anyone can just write in the chat and let me know like what you guys were like initially thinking when you saw this question. Like what do you guys try to do? You can just type in the Zoom meeting chat or like the Discord.
Yeah. Yeah, I enable chat for everyone, so you can type it in the chat. Trying to prompt.
Yeah, okay. That's in the correct direction. Like you want to bound in some way. But then so yeah, okay. That's another very good idea. As Sandesh pointed out, you want to try and Euclidean algorithm something. So when you see this divisibility condition, the first idea that should come to mind is maybe we want a Euclidean algorithm in some way and reduce the right-hand side to something that we can bound. But when you look at it, we have like A and B and a 1. And it's very hard to have like a physical sense of how big the number is, right? But then thankfully we have the condition A divides B. So how can we, yeah, correct. We can substitute B equals to AK, where K is some integer, positive integer, right? So what does that condition basically change the whole question to? It just becomes A plus AK plus 1 divides A square plus A square K square. In other words, A times K plus 1 divides A square times K square plus 1. And now, as Sandesh mentioned, we can use Euclidean algorithm on this, right? So if this condition is true, it means that A K plus 1 divides A square times K square plus 1 minus K minus 1 times the whole of the left hand side. Do you guys understand why this is true? This is because if the right hand side is a multiple of the left hand side, I can add or subtract as many copies of the left hand side as I want, and I will still be able to, and the right hand side will still be divisible by the left hand side. Someone asked for the motivation of doing this, and I'll tell you what. The motivation is that you see a case, sorry, we see a k squared plus 1 term here, right? So we want to somehow remove the k squared completely from the exponent a squared. Like we want to completely remove a squared k squared. And the closest we can get to it is this. Because this is just a times a k squared minus 1 plus k minus 1, right? Which is just a squared k squared minus 1 plus a k minus 1. So what happens when we subtract the whole thing? It becomes a k plus 1 divides the a square k square, the k square terms cancel out and becomes 2a square, right? Because minus 1 it becomes plus 1. Then we have minus a times k minus 1. Correct? But then we realize that we can completely factorize out a from the right hand side. We get a times k plus 1 divides a times 2a minus k plus 1. But then what's a key observation right now? The key observation is that this thing here is coprime to a. Do you guys get why it's coprime to a? It's because it is a multiple of a plus 1. So if you did a Euclidean algorithm on this, it will be is equals to the GCD of a k plus 1 minus a k plus 1 a, which is just GCD of 1 and a, right? So this can never divide a. Like it doesn't share any common factor with a. So we can just completely divide the right hand side by a. And we'll get that a k plus 1 divides 2a minus k plus 1. And we can go back to our fact 2.3, right? So we already know that k is a positive multiple, right? So k is at least 1 already, correct? Wait, I guess k can be 0 too. But if k is at least 1, we notice that the right hand side, sorry, the left hand side is larger than the right hand side. And this must be true because we have a k plus 1 is at least 2a plus 1. And which is larger than 2a minus k plus 1. But by fact 2.3, this cannot be true. Therefore, we must have that 2a minus k plus 1 equals, wait, sorry, the magnitude of the left-hand side. Yeah. So we must have that the right-hand side must be equals to 0. So this just gives us that k is equals to 2a plus 1. So b must be equals to a times 2a plus 1. Do you guys have any questions about the solution? So I'll summarize again. The main idea in the solution is firstly, you substitute b equals to ak so that you're utilizing the condition a divides b, and it becomes very easy to manipulate the whole like expression. And secondly, the next idea is that once you have a squared k squared term over here, right? We want to be able to find a way to eliminate it from the right hand side. And the way you do that is by using long division. And you try to factor out subtract away like a large as possible um k value. And in this case, you do so by multiplying by a times k minus 1. And after that, you get an expression like this. And the third learning point here is to identify that um, a times k plus 1 is coprime to a. And you have to be very quick to notice that. So I can give you an example. If I give you the number 3 and I give you like 10, 10 is a multiple of 3 plus 1, right? 10 and 3 are obviously coprime because once you divide 10 by 3, you get a remainder of 1. So you can think of the Euclidean algorithm as dividing the other number by the initial number and looking at the remainder and considering the greatest common divisor between the remainder and the original number. So if I divide by a, the remainder is 1, and therefore the greatest common divisor between the two numbers is 1. And when you can remove a and you know that it is not divisible or like it doesn't share a factor with the divisor, you can always remove it from the expression because this must divide this term, excluding the a. And the remainder of the solution over here is an application of how you use size from fact 2.3. The fact that um, if a divides b, then the magnitude of b is larger than or equals to the magnitude of a if b is not equal to 0. Because if b is 0, like anything can divide b. But if that's not true, this condition must hold. It's a very important condition for divisibility questions, and it's very useful when it comes to bounding by size. Yeah. Does anyone need me to go through like a certain part of the solution? You can just send it to the chat, then I'll try my best to explain. I'll give it one more minute. If anyone has questions, then I'll just move on. Okay, then I'll start going through problem number 2. Um, Question 2. So problem number 2 uses is let n b equals to 2 to the power of 2018 minus 1 divided by 3. Then prove n divides 2 to the power of n minus 2. Do you guys have any ideas as to how we would approach this problem? If you have any ideas, just send it to the general chat or like on the Discord general chat. Just shoot ideas. It's fine to be. Okay. Um Someone mentioned generalize and induction. I feel like that would be a very good idea, like for most problems, but in this case, I don't think it works. Someone said geometric sum of the powers of two. Um, that's a very good observation, but it's not applicable to this question. And yes, someone mentioned Fermat's little theorem, and that is indeed the route that you want to take for this problem. So, as I mentioned earlier, Fermat's little theorem is a very good tool when it comes to reducing very big powers like this into smaller powers. Like it's very hard to compute 2 to the power of 2018, let alone 2 to the power of 2 to the power of 018 minus 1 divided by 3. So the first observation here is that we will have that we let sorry, let 2 to the power of n be congruent to 2 to the power of r mod n, where r is a residue of n mod 2018. And our final goal is to show that r is basically congruent to 1, right? Because we want to show that n 2 to the power of n minus 2 is congruent to 0 mod n. And I think someone mentioned that we want to split the primes up as 1009 and 2. And that's a very good observation because you cannot do Fermat's little theorem on composite numbers. You must only do it on primes. So we consider n mod 1009 first, and we have n, n is congruent to 2 to the power 2018 minus 1 divided by 3 mod 1009. And we notice that this is congruent to 2 square times 2 to the power of 1008 square minus 1 divided by 3. And if you recall, 2 to the power of a to the power of p minus 1 is congruent to 1 mod p, right? So 2 to the power of 1008 is congruent to 1 mod 1009. So this is congruent to 4 minus 1 divided by 3, which is congruent to 3 over 3 mod 1009, which is congruent to 1 mod 1009. What about mod 2? N is congruent to 2 to the power of 2018 minus 1 divided by 3 mod 2. what do we notice? The top here is an odd number, right? And the bottom here is also an odd number. So an odd number divided by odd number should give you what? Odd number divided by odd number should give you an odd number also, right? And odd numbers are 1 mod 2. So these two results will basically give us that n is congruent to 1 mod 2 times 1009. Which is congruent to 1 mod 2018. Correct? So how do we finish with n being congruent to 1 mod 2018? It's that we notice firstly 2 to the power of 2018 is congruent to 1 mod n. Do you guys agree with this? It's because we have that 2 to the power of 2018 minus 1 divided by 3 is congruent to 0 mod n, right? Because that's the definition of n. So it implies that 2 to the power of 2018 minus 1 is congruent to 0 mod n. And therefore, it gives us this result. So the result that 2 to the power of 2018 is congruent to 1 mod n basically allows us to make this assumption. Because if we have 2 to the power of n is congruent to 2 to the power of n minus any multiple of 2018 mod n. Hence, we can take R to be some residue of n mod 2018. So since n is congruent to 1 mod 2018, it implies that 2 to the power of n is congruent to 2 mod n, and hence 2 to the power of n minus 2 is divisible by n. Do you guys have any questions about the solution? I think the Fermat's little theorem portion of the solution is a bit more straightforward. But the harder part about the solution is noticing that n is actually okay, the n is a bit confusing. Okay. Maybe I will try to re-explain it. So okay, your first wait, you guys firstly agree that n is congruent to 1 mod 2018, right? Like, do you understand the Fermat's little theorem proof? Like this part and this part, correct? So we've established this fact. Like, this fact is true. Obvious by FLT. So now the question is, how do we show 2 to the power of n minus 2 is congruent to 0 mod n, correct? Okay, so the way you do this is firstly notice 2 to the power of 2018 minus 1 over 3 is congruent to n mod n. And then this is congruent to 0 mod n, right? So what can we do? We multiply both sides by 3, and this gives us 2 to the power of 2018 minus 1 is congruent to 0 mod n. Do you guys agree? So now we move the 1 to the other side. So we have 2 to the power of 2018 is congruent to 1 mod n. You guys with me until here, right? So we have this fact. So now we let n be equals to like 2018 a plus b, where b is less than 2018 but larger than 0. So um so we have this fact, right? So if this is true, then we have 2 to the power of 2018 a plus b is congruent to 2 to the power of 2018 a multiplied by 2 to the power of b, which is congruent to 2 to the power of a 2018 to the power of a multiplied by 2 to the power of b, which is congruent to 2 to the power of b mod n. And what is 2 to the power of b mod n? We notice that n is equals to 2018 a plus b, which is congruent to b mod 2018, correct? Hence, so since n is congruent to 1 mod 2018, implies that 2 to the power of n congruent to 2 to the power of 1 mod n. Are you guys clear of like the link to the last part now? I think it was harder to see initially, but now if you think about it through this logic, you can think of it as once you have 2 to the power of 2018 is congruent to 1 mod n, what you're basically doing is just removing multiples until you reduce it to n mod 2018, which is just 1. Yeah. So this is not the easiest application of Fermat's theorem, but it's the hard part in this question comes to how you're able to use the information that n is congruent to 1 mod 2018, because that's not a very direct like application of it. Okay, so what's the next question? Once you guys are done, like I'll give you guys some time to like interpret the like solution, and now I'll start um going through problem number 3. Okay, so I'll start going through problem number 3 now. So the question says find all A, B satisfying, firstly, B minus 1, sorry, A plus 1 divides B minus 1, and the second condition being B divides A squared plus A plus 2. Do you guys have like any ideas as to how we should approach this question? Right. This problem seems quite similar to um question number 1, right? So like your first idea or thought maybe, okay, maybe like since we have two divisibility conditions and A is on the left hand side for one of them and right hand side on the other, maybe we can do some bounding and find some size condition from the bound, right? So that's exactly what we will try. But before we start doing that, um, one thing that we might want to think of doing is letting A plus 1 B goes to C. And like you don't really have to do it, but it's just because um it's easier to work with and manipulate because you want the divisor on the left hand side over here to be some nice expression so that you can manipulate it more easily later on. So if we let A plus 1 B equals to C, then A squared plus A plus 2 is equals to um A plus 1 times A plus 2, right? Which is C times C minus 1 plus 2, which is C squared minus C plus 2. So what conditions do we have from um this first condition over here? The first condition rewritten is that C divides B minus 1, right? And what did I mention earlier? Um, if C divides B minus 1, GCD of C and B is equals to 1. And this is exactly because GCD of C and B is equals to GCD of C, B minus B minus 1. And this is because by the Euclidean algorithm, right? Since C divides B minus 1, B minus 1 is a multiple of C. And you're able to minus will be multiples of C from B, right? And this just gives us GCD is just C and 1, which is equals to 1, which basically explains why it's coprime. And at the same time, uh, we notice that we have the condition B divides C squared minus C plus 2, right? And we want to somehow make it such that like C also divides the expression over here. And the motivation for doing that is because if you think about it, the size of the left-hand side as compared to the right-hand side should be approximately the same in order for us to carry out some sort of size bounding. But currently, the left-hand side is like a degree 1 expression, and the right-hand side is like a degree 2 expression, right? Because we have a c squared term. So in some sense, the right-hand side is still bigger than the left-hand side. And the way we can make the left-hand side a degree 2 expression is by noticing that B also divides c squared minus c plus 2 minus 2b. You guys agree? And what is this? This is equals to c squared minus c minus 2b minus 1. And what do we have? Condition 1 states that C divides B minus 1, right? So this is divisible by C. But at the same time, this is also divisible by C. And we know that B and C are coprime. Because this implies B and C are coprime. So if B divides this expression and C also divides this expression, it must mean that BC also divides this expression, right? Do you guys agree? And if B goes to 1, obviously, um, like there's like infinitely many solutions, right? So supposing B is not equals to 1, i.e. B is larger than or equals to 2, what solution set do we get? If B is larger than or equals to 2, it implies that C is less than B, correct? It's by our fact number 2.3, where since C divides B minus 1, it implies that, and B is larger than or equals to 2, we have that B minus 1 is larger than or equals to C, so B is larger than C. And what happens if B is larger than C? Note, BC is larger than or equals to C squared. Hey, sorry, is strictly larger than C squared. Do you guys agree? And what more is that C squared is also strictly larger than C squared minus C minus 2B minus 1. Correct? So what does this mean? Firstly, this um is not like a negative number, right? Because C squared, in order for this to be a negative number, it implies that C squared minus C minus 2B minus 1 is strictly less than or equals to minus BC in order for it to be a negative number. Because this is a possibility. Wait, no, no, no. Ayama, like, it would eventually lead to that, but we need to show that negative numbers do not work first. Okay, so in order for it to be negative, this must be true. But then, can this even be true in the first place? The fact is, this like can't even be true because we notice that C squared minus C plus 2. Wait, note that this is equals to C squared minus C plus 2 minus 2B, right? And this is definitely positive because this is C minus half square plus um 2 minus 1 over uh wait 7 over 4. Yeah, yeah, yeah. So this is at least 7 over 4, right? So this is definitely positive. So this is um less than or equals to minus B, minus 2B, which is clearly larger than or equals to minus BC, right? So this cannot hold since these two are equal, but we have a strictly larger than sign here. There's no equality. So this means that c squared minus c minus 2b minus 1 is equals to 0. Since it cannot be a negative multiple, neither can it be a positive multiple. So it strictly equals to 0. So we have c squared minus c plus 2 is equals to 2b. Okay, so what do we substitute c to be initially? We let a plus 1 equals to c, right? So a plus 1 square minus a plus 1 plus 2 is equals to 2b. And this is a squared plus 2a plus 1 minus a minus 1 plus 2 is equals to 2b. So you have a squared plus a plus 2 is equals to 2b. So as long as a is even, there is always a solution to b. So the solution set is ab is equals to 2k, and then it will be 4k squared. So it will be 2k squared plus k plus 1 for all k that is uh, a positive integer. Okay. So what was the main gist of the solution? The main idea was to firstly identify that we have that b minus 1 is divisible by a plus 1. And we want to somehow exploit this fact, right? And that's what motivated us to make the substitution a plus 1 is equal to c. Because with this divisibility condition, if we substitute c instead, we have that c is coprime to b. So notice that in divisibility questions, the coprime condition is very useful because making something coprime allows us to firstly do stuff like this, where we can easily manipulate the left-hand side of the divisibility sign. Either that, or we can completely factor out like the coprime factors and remove it from the division as we did in problem 1. So when you see potential coprime stuff, make sure you exploit it or find substitutions to exploit the coprime condition. And secondly is to find ways to make the size bound possible. Like at first glance, like this doesn't seem like very size boundable. But then once you make the degrees of the left hand side and right hand side the same, so this becomes degree 2, and this is degree 2, right? Size bound is very possible. So even when at first glance size bound doesn't seem possible, try to make ways to increase the size of the divisor in order to make it possible. And on the size bounding itself, do not forget to check the possibility that the right hand side might be negative also. So when size bounding, always make sure to consider the cases where right hand side is firstly positive. I mean, this is the most like obvious case when right hand side is equal to 0 and when it's negative. What we generally want to do is we want to make the right hand side 0. So we want to show that it cannot be positive and it cannot be negative. And we must remember to show it. A very easy way to show it sometimes is to show that the modulo of the left hand side is larger than the modulo of the right hand side. Then it covers both the positive and negative cases. And it just gives us that the right hand side must be equal to 0. Yeah. So do you guys have any questions about problem number 3? Can you please clarify where we ruled out odd solutions for A? Oh, we ruled out odd solutions for A Um, uh, it's because if A is odd, wait, give me a second. Mm, um, if A is odd, wait, sorry, give me a moment. Wait.
Yeah, I think it can be odd too, because
Wait,
odd plus
no, that
even is even.
A cannot be odd though.
Okay. Someone here says 3, 7 is a solution.
I don't think wait, 3, 7 is not a solution because 4 doesn't divide 6.
Oh, okay. I haven't really looked at the questions, so I guess not.
Um, if okay, wait. Then let A equals to 2k plus 1. Then we have uh 2k plus 1 square plus 2k plus 1 plus 2 equals to 2b, correct? Then we have 4k squared plus 4k plus 1 plus 2k plus 1 plus 2 is equals to 2b. Then we have 4k squared plus 6k plus 4 is equals to 2b. Then we have 2k squared plus 3k plus 2 is equals to b. Then we'll have that uh this is so b minus 1 is divisible by a plus 1, right? 2k plus 2. And if you long divide this, we'll get k and 2k squared plus 2k, and then we'll get k plus 1, right? But then obviously um k plus 1 is not divisible by 2k plus 2. So a must be even. Sorry, a must be, yeah, even. Odd doesn't work. Yeah.
Yep, that works. 4, 11 can be solution. Okay.
Four 11 can be a solution. 16 plus
Yeah,
4.
yeah, it can be. It does work.
Yeah, but it works because A is even.
Yeah, yeah.
Yeah, so like only A is even as a solution, right?
Mm-hmm.
Yeah. Like A is odd doesn't work. Um, I think a shorter explanation could be done by considering mod 4, maybe. Because wait, yeah, yeah, yes. So A odd doesn't work. You guys can read like the proof to why A odd doesn't work over here. Yeah, like B equals to 1 gives you infinitely many A solutions. I mentioned that earlier, I think. Yeah. I just suppose this because B equals to 1 is a trivial solution to yeah. Yeah, you have to include it. You have to state that it is a solution first.
Um, I think you are assuming that A and B are both greater than one. I mean, B is greater than one for this part, right?
Yeah, no. So when you start this problem, you must write um note B equals to 1 uh gives their solution set A B equals to x1 for all x that are positive integers. And that's obviously true because x divides 0 and 1 divides x squared plus x plus 2, right? So after this, we just state that now consider b not equals to 1. So b is at least 2. And then the rest of the proof works.
Yeah, let's proceed.
Okay, I'll move on to problem number 4 now. I think
Mm.
this problem is quite neat. Do you guys have like any ideas for how you do problem number 4? So A, B, C are natural numbers, and then prove that if AB divides A to the power 4 plus B to the power 4, and BC divides B to the power 4 plus C to the power 4, then AC divides A to the power of 10 plus C to the power of 10. If you have any ideas, you can just like write it out on the general chat. Binomial expansion. Um, Not really, because it's like very hard to uh it's quite hard to do binomial expansion on it. Actually, it's something much easier than that. And it's by considering the greatest common divisor of A, B, C. Or I think I saw the chat just now, the highest common factor, like HC, I think. But I also call it GCD. So let uh let the GCD of ABC be equals to um uh X, for example. Then let GCD of AB divided by GCD of ABC be equals to Y. Wait, never mind. XAB. GCD of AC divided by the GCD of ABC be equals to X AC and GCD of BC divided by the GCD of ABC be equals to XBC. And let A prime be equals to A divided by X times XAC times XAB. Do you guys know why these are all integers? Um, so right. So GCD of A and B has to be a some multiple of GCD ABC. And next, XAB and XAC, they're coprime. Because suppose X GCD of XAB, XAC is not coprime. Like there's some divisor D that divides the greatest common factor of this, which means that there's in fact actually D divides GCD of ABC, correct? But that cannot make sense since um, D divides GCD of AB divided by GCD of ABC. Since like the GCD of ABC at the denominator should have divided out all possible like greatest common factors, right? So contradiction. So like everything here must be integers. So we let A prime be equals to this and define B prime and C prime similarly. So A is equals to X times XAC times XAB times A prime. B equals to X times XAB times XBC times B prime. C equals to X times XBC times XAC times C prime. So what does our divisibility condition give us? So AB divides A to the power 4 plus B to the power 4 implies that X squared times XAB squared times XAC times XAB times A prime B prime divides X 4 XAB 4 XAC to the power 4 A prime to the power 4 plus XBC to the power 4 times B prime to the power 4. Do you guys agree? This is just rewritten, right? So what does this basically imply? This implies that x AC, x BC, wait, sorry.
I'll answer the things on the chat.
Okay. X BC times A prime B prime divides x square x AB to the power of 4. A to the power of 2. And this is because XAC, XBC cannot divide this. And can you guys see why? Wait, you can refer to the XAC, XEB on top. And do you guys know why this cannot divide this? It's because XAC, XBC are pairwise coprime, which implies XAC does not divide XBC to the power of 4, B prime to the power of 4. So the left hand side cannot divide the the right blue stuff. And similarly, as you define, A prime and B prime are pairwise coprime. So the other divisibility condition, which is BC divides B to the power of 4 plus C to the power of 4, implies that X AB X AC times B prime C prime divides X square X BC squared. And moreover, since we know that our X A X AB X BC are coprime, like these two are coprime, and also these two are coprime. We can reduce this into X AB divides X squared. And similarly, X BC divides X squared and X AC divides X squared. Do you guys get the reasoning? It's from comparing these two. Right. So what do we have? So we want to show this, right? But what is AC? AC is equals to X X AC X AB A prime times X X AC X BC C prime, which is equals to X squared times X AC squared X AB X BC A prime C prime. Correct. And this is basically equals to our so this basically using these three uh conditions, and we apply it on both this and this will just give us that this divides x square x ac square times x square x ab square times x square x bc square. Do you guys agree?
Yep.
And we finally utilize this to give us this divides x um x square times x ac square times x square times x square times x square two times because we transform xab and xbc into the x square terms. And what's this? It's x to the power of 10 times x ac square, right? Which divides GCD of AC to the power of 10. Correct? And what's this? It's just A to the power of 10 plus C to the power of 10. Sorry, it's not equals to, it divides. Yeah. And that's the gist of the solution. Actually, I feel like this problem is not a very hard problem. Like, what this problem requires you to do is identify that it's a greatest common divisor type problem. And you constantly exploit the like divisibility conditions given. And I mean, you should suspect it when you see the power of 10 conditions, right?
Mm-hmm.
Um, when you constantly um extrapolate on your initial GCD conditions, you can extend it onto the power of 10. This just requires you to like grind out the divisors and the divisibility conditions until you uh get it. The problem feels cumbersome. I mean, um, that's Olympiad problems in general, right? Like as you go higher up, um, in the like difficulty, you should be thankful that a problem is more cumbersome, because a more cumbersome problem means that you require less thinking and less brain power and more of like doing of the problem. Because it's much harder to think of new solutions as compared to sitting down and really putting in the effort and working out the whole process to get the solution. So it's either like um the problem is elegant and short, but it's very hard to think of the solution, or the solution is like very long and like detail oriented, but it's how do you say, more direct to get. Yeah. Do you
So,
guys want me to go through the advanced problems or
so I wasn't looking at the solution, but can you guide me like why does this GCD of A comma C power 10 divides A 10 plus C 10?
uh
What do you, yeah, this one.
because if GCD AC equals to D, then A equals to DA prime and C equals to DC prime, right?
Yeah.
Then e to the power of 10 equals to,
Okay. Yeah, yeah, I get it.
so you have a factor of d to the power of 10.
Hmm. Oh yeah, obviously. What I was thinking. Um, okay, so oh okay, yeah, I got it.
Yeah.
So okay, yeah. But okay, so if I did this problem, I wouldn't like approach it this way. So what's your motivation behind like going this way for this problem? Because like initially I was thinking maybe doing some Euclidean algorithm like subtracting and factoring out and then probably multiplying
Because
and
you realize that Euclidean algorithm will bring you nowhere because
mhm,
you have like a b term on your left hand side and we have some exponent, right?
mhm,
Like Euclidean algorithm, firstly, you won't be able to eliminate the e to the power of n term. And I feel like a more intuitive approach, right, would be to think, okay, if AB divides this, it means that firstly A divides this, right? And secondly that B divides this.
yeah,
So A must divide B to the power of n, B divides A to the power of n.
okay, yeah,
And once you go down this route, it's very hard to come up with like a sort of like a good like size bound or like any good intuition other
mhm,
than the fact that they share the same sort of like prime factors. So
mm,
um the next approach from here is to try and like uh separate out, like group up the different factors that A and B has.
yeah,
And the best way to separate it is in terms of the GCD that it has. So that um we can focus on the factor that is coprime to our other factor, right?
okay,
Because shared factors can just be ignored. So that's like the logic behind it.
hmm.
So
So yeah, so I guess it just comes from intuition and practice, right?
yeah,
Because
yeah, yeah.
like when I saw the variables, like I got up to this GCD thing, like they have to have some sort of same GCD and then it will divide. But like this XAB, XAC, and XBC completely threw me off. And then this A prime, you know,
Oh,
I turned on a similar problem, so
because
it's kind of
it's
something
like
new to me.
we use the GCD. The problem with it is that okay, um, like if I just use like the normal GCD, right? I do like GCD. Like if I let A equals to GCD, something like this. The problem with this is that the GCD of AB and the GCD of BC, like these two things don't have to be coprime. They can share
Hmm.
a common factor.
Yeah.
And that is problematic because we want to be able to express A, B, and C as a combination of coprime factors.
Mm. Okay.
It's the whole point of using GCD in the first place. So if there is like some sort of like shared factor between the two GCDs, it
Hmm.
defeats the purpose of using GCD in the first place.
Yeah. Yeah.
Yeah,
Yeah, then that makes sense. I mean, if I see a similar problem, I'll probably approach it this way. Any particular reason for using A prime? So we can express A in terms of this multiplication of GCD and
yeah,
the prime.
yeah.
That's
Because maybe like A has some unique prime that B and C does not have, right? And
Mhm.
we will need to include that in the product. So we must have a A prime term.
Yeah. Okay, so I guess we're doing this much for today. I'll open up the voice chat if in case someone wants to ask any question.
Yeah, sure. Yeah, the session is recorded. For the advanced problems, like if you try it and you want to like read the solution, just uh ping me on the general chat. Then I will like uh write up the like solution like either on the chat or like I'll publish it later on.
Mhm. Or we can do a separate class for this. Like, the next class we could solve the advanced problem.
Yeah.
I mean, everyone should try doing the advanced problems, and then for the next class we'll try to do the advanced ones.
Hello, excuse me, sir.
Yeah.
Sir, I'm not understanding this little question. From where I can start the basic, sir.
Sorry, can you repeat the question?
Uh, he means like he does not understand the basics of it either. I think the best way is to like uh read some number theory books for the basics.
Oh, like he doesn't understand like the basics of number theory, such as like modulo and stuff.
Hmm.
Then I can suggest some like books or like handouts to I think I sent the Modern Olympiad Number Theory book.
Yeah, yeah, you did. And then most of them had haven't checked it out. I guess
Yeah, under
like yeah.
notes and resources.
Hmm.
So I linked the Modern Olympiad Number Theory book. So I think the first few chapters, that's like a very comprehensive explanation of all the basic number theory. So if you have any questions, even after reading that, then you can ask in general, then I'll like respond to it and like explain some of the questions that you may have.
Okay. Yeah. Um, does anyone have any questions? How to find motivation? That's something you have to work
Uh
on.
motivation. Wait, I think I
Okay. Yeah. Okay. Sorry. Now
went
has
like last session. So as I said, like motivation like doesn't just like come out of the blue. It's uh primarily by like pattern recognition because of certain features about the problem, right? So as I said, it's something that you have to build. So after you finish your problem, ask yourself like what was the motivation behind this solution. So we went through four problems today, right? So if you wanna like be able to develop like motivation, I would suggest that after we finish the session, go and give yourself like 15 to 20 minutes. Just think to yourself, how did how did Taeyoung or how did like whoever solved this problem think of the solution? Like what part of the question made him go down this path? And what motivations were wrong? Like what did I try that didn't work for this problem? And you can like uh note it down like into like a notebook or like just mentally note to yourself, I tried this, it didn't work. So in the future, if I see a similar problem, I won't go down this path and waste time, but instead try the path that I've seen before or like new ideas that I think of and just keep building the intuition behind the motivation. How can one develop intuition quickly? You just have to do like a lot of problems. Like it's not something that you can build quickly, I guess. Uh, did you create these problems yourself? If not, how long? Okay, so I did not create these problems myself. These problems are problems from different Olympiads. Um, do you get many dead ends while solving? So I'll firstly tell you like how long I took to solve them, I guess.
You don't have to answer like, bullshit questions.
So obviously I do face dead ends when I solve the problem. Like I'll think of a certain approach, then wait, so my thought process when solving the problem is when I first see the problem, I'll have like 3 to 4 potential approaches to solving the problem. Then I'll start by doing the one that seems the most promising. And whenever I realize that it's probably not gonna work out, I just go to the next best approach and just keep going on, I guess. Yeah. Uh, and I do not meditate. How to be better at math? Just do lots of problems. Um, discuss about problems with your friends, and just keep thinking of math problems, I guess. Yeah. Um, yeah. That's how much can extensive for Olympiad calculus does like little to no help. Like it doesn't really help you much at solving Olympiad problems, but it may allow you to use some like more advanced techniques like Lagrange multipliers or maybe some like inequality problems, but it doesn't really help for functional equations, in my opinion. Yeah, it develops intuition. Like you can bound also, but then um, I'd like to warn you guys from using too much high-powered stuff to solve problems because sometimes it just overcomplicates it and it like clutters up the whole solution. So you may end up like straying away to like a much harder solution when you have like a much easier one right in front of you. Any other approaches to solving um uh these problems? Definitely. Like there's always more than one solution to solving Olympiad problems. Uh I'm sure that you can find other solutions, and if you come up with your own solutions and you think that it's right and you want someone to check it, you can just ping me in the general chat and I'll read it for you.
And anyone asking for the simple solutions, like try going over these problems once again. Like see if you can recall anything from the video and try solving them yourself. I think that kind of develops an intuition too. Similar to complex numbers of Barry. Are these brute force methods?
Uh not really. Like number theory, you just have to gain good intuition and just like solve it properly. There's no like cheat method or like bash method for a number theory. You just have to solve it as it is. I'll take like 2 more questions, then I think we can call it a night.
Um, yeah, Opil has told me that the recorded video will be available soon. So I'll post it in the Discord, on the Discord. Yeah,
Okay, I don't think there's like any questions left.
yeah. Thank you. Thank you so much for taking this class.
No problem.
Good night.